Assalamu alaikum. The estimation of the required sample size for a certain study is often governed by practical considerations, like availability of resources in terms of time, money, availability of patients or specimens, and so on. But when conducting studies on certain measurements or certain comparisons and a defined confidence level is required, and a certain margin of error, then equations are required to estimate the exact sample size to avoid wasting of resources and time in studies that may not show significant results at the end. In this presentation, we'll go through 8 different scenarios using different equations and different modifications to these equations to calculate the required sample size. This will include studies for a single group measurements with continuous data, single group compared to a standard, again with continuous data, single group estimating a certain proportion or a percentage with dichotomous data, a single group study with proportions compared to a standard, controlled studies where there is at least two different groups, continuous data, either with independent samples or matched samples, and controlled studies with dichotomous data, and finally, when we are dealing with studies in a finite or a known population rather than infinite population. We start with the first scenario in which we are trying to measure with a certain degree of precision and confidence a continuous outcome like a length or a volume or a certain hormone level, one continuous outcome in a single group study. Before starting a study on a single group measurement, we want to know the number required, and 3 factors would influence this. The number required N is related to the level of confidence that we want in our results, the variability of the measures within the group that we know from previous studies, from the literature or from pilot studies, because we have not yet started our own study, and the margin of error that would allow for our measurements. The margin of error is set by the investigator. The level of confidence is also set by the investigator, and the variability, the standard deviation, is taken from pilot studies or previous studies. And the 3 factors would give us the required sample size so that at the end of the study, we would have enough precision in your measurements to give the average, say for example 12 millimeters of a certain distance, and a margin of error, say about 1 plus or minus 1 millimeter plus or minus that average, with a level of confidence of 95%, for example, or 97 point something, or whatever you set out the confidence level and the margin of error. And that applies to all measurements for continuous data, lengths, weights, and time and things. The confidence level would tell you if it is 95%, for example, that if the study is repeated 20 times, 1 in 19 times of the 20, your estimation of the margin of error and the average would fall within this line, which resembles the actual population mean. So you know that you have a high level of precision in your estimations. To take an example, say we are setting up a study to measure the distance between the posterior ethmoidal artery and the optic nerve in adults. We want to know exactly what is the distance, the average distance, and we will set the margin of error that would allow for, and that should be as narrow as possible. Say we choose to 1 millimeter because it is surgically important to have a very precise estimation about the distance between these two structures. You would allow only for a very narrow margin of error, and you want to be very confident about the results, so you choose a 95% confidence, so that if this study is repeated 19 out of 20 times, you would have within your margin of error, you would have the correct estimation here. All of these 19 different studies, only one study would have the margin of errors around the average outside the correct answer. So we start with the equation, and there are three variables here that would need to be identified. The first is the level of confidence, and we have chosen 95% level of confidence. The z-score for this is 1.96, so we'll put here 1.96. The standard deviation of the measurement between the posterior ethmoidal artery and the optic nerve from previous studies or from pilot study should be about 3 millimeters, so that would be plugged into here. And the margin of error that we have chosen, because we want to be very precise, would be 1 millimeter, and that would fall into here. And the equation would then be this amount would be squared, and the required sample size would be this 34.57. This is the minimum, so the actual number of cases, either patients or surgical skulls or surgical specimens required, would be 35 cases. Now, the second equation to estimate a sample size for a different scenario is this. It's the equation needed if you want to compare measurements in one single group with a standard, a known standard. Say if you want to measure a blood pressure, systolic blood pressure of a certain group, you can do this with only a single group. You don't need to get a control to compare it with, because it's already known. The systolic blood pressure in the adults is already known. It's a known standard. So you can afford to have only one group and compare it with the known standard. The equation, again, depends on three factors. How much you would allow for type 1 error. This is the level of confidence you would choose. How much you would allow for type 2 error. This is how much power you need for this study. And the effect size, which is the difference between your group and the standard measurements divided by their standard deviation. So if you have a group which is quite different from the known standard, then you would have a higher effect size. If it is very close to the known standard, then you would know that it has a smaller effect size. The distance between the average of these two groups divided by their combined standard deviation would give you the effect size. So this is the second equation to measure sample sizes. So for example, if we are investigating the systolic blood pressure of adult epistaxis patient, this is an example of analyzing continuous data from a single group. You can do one of the two types, use one of the two equations. If you just want to get measurements, precise measurements of the systolic blood pressure in this group, then you use the first equation, and then you will be able to tell that the systolic blood pressure, for example, is 140 millimeters of mercury with a 5 millimeters mercury margin of error with a 95% confidence level. You get this out of this equation. This equation, which depends on the margin of error, the level of confidence, and the known variability and the blood pressure of this group. Here we set the z-score, the level of confidence, again at 95%. So z-score of 95% confidence interval would be 1.96. We'll plug this here. The variability and the systolic blood pressure in epistaxis patient or in patients in general known from the literature or from pilot studies would be somewhere around 20 millimeters mercury. So we'll plug this into here, and the margin of error that we want to allow or can allow would be, say, 5 millimeters mercury. We set up this level as much as we set up this level as well. So we'll plug in here 5 millimeters. So the equation will be 1.96. This is here multiplied by 20, the standard deviation that we have found in the literature or from pilot studies, divided by 5, which is the margin of error, all squared. This will give us 61.546, i.e. the required sample size would be 62, at least 62, because we'll have to consider patients who may be lost to follow-up. So that's the first equation for the continuous data from single specimen. The other equation is this. Say now we have found out the blood pressure of the adult epistaxis patient with a good precision in the measurement, but we're now interested to see if this systolic blood pressure is higher or lower than normal. Then we compare it to a known standard, and that known standard is fixed through the literature, the systolic blood pressure of adult patients. So we here compare our measurement with the known standard and find out if there is a significant difference or not. And for this, we need the required sample size, which depend on the 3 factors: the level of confidence here, 95% again, and the power of the study. Here we have chosen 90% power of the study, which translates to z-score of 1.28. So we plug this here as well, divided by the effect size. Now, how can we measure the effect size? And with a single group, we subtract the average of our group from the known standard. Say if we have measured the systolic blood pressure and the epistaxis is 130, the normal systolic blood pressure in adults is 120, so that amount would be 10 millimeters divided by the known standard deviation, again from the literature or from the standard, and that's 20 millimeters mercury. So if you divide 10 by 20, this is half. Effect size here is half. So we plug in 1.96 here, which corresponds to the z-score of 95% confidence, and the power 90% is 1.282 divided by half here, and this would give you the result. Required sample size is 42.04, which is 43 patients. Another scenario here. We're still using the single group study model. We're studying only a single group, but this time we will be measuring dichotomous data rather than continuous data. Things like alive, dead, success, failure, positive for certain tests or a negative for certain tests. These are dichotomous data. We'll be using the data for one of 2 types of studies. The first is when we try to estimate a certain ratio or a percentage in a population, like the incidence of a certain disease or the prevalence of a certain disease or a certain complication of an operation. And the second is when we are trying to compare this ratio or this percentage that we have found in a single group to a known standard. We're not using a control group. We are comparing what our findings to a known standard. So starting with the first thing, the precision of our estimate. How accurate is our estimate of the percentage of the intratympanic facial nerve canals that were actually found dehiscent during our study? At the end of the study, we would produce a report with these 3 figures in it. The actual outcome, this is the number of the facial nerve canals that were found to be dehiscent during the study, X percentage, say 20% or 25% or whatever, plus or minus the margin of error of our estimation. And this is something that we set at the beginning of the study. We set out this margin of error, and we set it out to be low enough so that with a small margin of error you would have more precision, but also practical too, because if you reduce this margin of error to a very low level, you would need more specimens to do your test. The same applies to the confidence level. You would want to set something like 95%. This is high enough and also adequate, and you would find to find out the correct answer. A 95% confidence interval, for example, would mean that if this study is repeated 20 times, 19 out of the 20 studies, that is 95% of the studies, would have the correct answer within its margin of errors. So this is a high level of confidence, and this is a fairly narrow margin of error. Now, the equation to obtain this is this. The number required, the size of our sample, would be related to three things. We start with the Z. This is the Z score of the level of significance that we have chosen. If we have chosen 95% confidence in a level, then the Z score for this will be 1.96, for example. The E would reflect the margin of error, and this would be 5%, and the P is the percentage of the population with or without the efficient nerve dehiscence. And obviously we don't know these figures before doing the study. We are setting the study actually to find out the actual proportions, but we can have a rough estimate or a rough guess about the population, the percentage of those who will have a dehiscence or not, from previous studies, from the literature, or from a pilot study. If we have this information, this would help. You can say if you find from a pilot study, for example, that 30% of the specimens have a dehiscent facial nerve, then P would be 30, and 1 minus P would be 70, and multiplying them together then it is one step for obtaining the sample size. If we don't have that information at all, and there had no previous studies and no pilot studies, then we assume that the percentage is 50% with dehiscence and 50% without dehiscence. The advantage of this is that this will produce the highest possible number that will be required, so that would be a very conservative way of obtaining the correct answer. So let's plug in the figures in this equation. The P, because we don't know, would be 50%, and the 1 minus P would be also be 50%. So that's 0.5 here, and 1 minus 0.5 is 0.5 again, multiplied by the Z score for the level of confidence, which is 95%. So that is 1.96 in here, divided by the margin of error, which is 5%. So that's 0.05 here, all squared at the end. So this will bring out this figure, 384.16. So you need at least 385 cases, specimens, or patients as a sample size to obtain the required information with a margin of error of 5% and a confidence level of 95%. Moving now to the next scenario. In this scenario, we would want to compare results obtained from a single group study, a proportion or a ratio from this single group to a known standard. In this study, there is no control group because this is a single group study, but we compare our results to a known standard, an accepted level that has been published and accepted. For this, we have a new equation, and this equation for estimation of the sample size would depend on three things here. The first, the z-score of the level of significance that we set at the beginning of the study. If we choose a p-value less than 0.05, this means that we have a level of significance of 95%, for example, for a two-tailed study. The second factor is the power of the study. How much are we able to tolerate a type 2 type of error? It's usual to have a power of the study of about 80 to 90% power. If it is 80%, the z-score will be 0.84. If it is 90% power, the z-score will be 1.282. And we add these two z-scores and divide them by the effect size. How different are the results from our study from the known standard? The more different it is in terms of how many standard deviations between the two averages, the more the effect size. The closer this is to the known standard, the smaller is the effect size. And the effect size would be calculated from this formula, which we'll come to it in a second. So this is an example of comparing a percentage, a rate, a ratio, or a proportion that we have obtained from a single sample study with no controls to a known standard that has been published and accepted as a standard. We are comparing the postoperative bleeding of a new tonsillectomy technique, for example, to a known standard of the postoperative bleeding in tonsillectomy operations. And for this study, we choose a p level of less than 5% and a power of 80%, and we want to detect a difference of 5%. So these are the figures that we are going to plug into the formula, and this is the formula to find out the required sample size for such a study. The required sample size for this study would depend on the p level that we have chosen, the 5%, the less than 0.05, the power that we have chosen, which is 80% translated into a z-score, divided by the effect size. And to calculate the effect size, we have this formula, which depends on the expected proportion that we expect to find in our study, or that we have found in a pilot study, compared to the known standard. So we start with this. The z-score for the level of significance at 95% is 1.96. This will be plugged in here, and the z-score for the chosen level of power, 80%, will be 0.84. Now, to estimate the effect size, we want the known standard. This is the P0, and say this is 10% expected rate of postoperative bleeding in tonsillectomy, and this is the standard that has been published repeatedly. The new operations claim that it would reduce this to 5%. So that's the P1, the other proportion. And the effect size from this would be the P1, the 5%, and the difference between the P1 and the P0, that's the difference between 10% and 5%. And this would be 5%, this is 0.05, divided by the square root of P1, which is 5%, multiplied by 1 minus 5, this would be the 0.95%. And these, the product of these two would obtain the square root of it and divide the difference between the two proportions by that square root, and the effect size obtained was 0.23. We plug this into the equation, plus the 196 here and the 0.84 here, so that the equation now with the figures plugged in the required sample size will be 148.1. That is to say, the minimum number of patients required for this study to obtain a difference of 5% between the rate of bleeding and have a level of significance less than 5% and a power of 80% would be 149 patients. We now move to a different study design. We're now trying to estimate the sample size for studies that are controlled. There are at least two groups here, a study group and a control group. And we are first trying to analyze the sample size for continuous data, and then we move to dichotomous data. We are dealing here with controlled studies with at least two groups of independent samples or matched samples. The outcome is continuous, as if you are, for example, measuring lengths, whether surgical or by imaging or certain pathological specimens, volumes like amount of bleeding, time like survival duration or hospital stay, measuring some vital signs, whether it's blood pressure, oxygen level, pulse, or laboratory findings, whether we are interested in measuring hormones, enzymes, or tumor markers. They are all continuous data, and the formula is the same. This is one formula used for estimating the required sample size for a controlled study, continuous outcome, continuous data. The number required in each arm of the study for each group will depend on three entities. The first relates to how much you can tolerate a type 1 error, alpha. The second, how much you can tolerate a type 2 error, beta. And the third is reflects the effect size, how much difference you would expect between the two groups in terms of their standard deviations. The first entity, by far the commonest level of significance chosen for medical research, is p equal or less than 0.05, and this translates to a z-score for a two-sided study of 1.96. So you see this 1.96 being used repeatedly in several equations. The second z-score is related to the power, and the usual in medical research that we use either 80% power or 90% power. If we use the higher power, of course, then we need more subjects in each group. Well, if we can do with 80%, then we'll have a smaller n. The z-score for the 80% is 0.84, and the z-score for the 90% is 1.28. So these two figures, you will see them repeatedly used. The 1.96 and either 0.84 for 80% power or 1.282 for 90% power. The third entity is the effect size, and this is basically how much difference you expect between the two groups divided by their pooled standard deviation. The higher the effect size, the less number will be required for each sample in each group, and vice versa. We'll go through how to estimate the effect size in the next two slides. Remember that we are trying to estimate the expected effect size before we start the study. So we don't really know how much of an effect size it will be, but we try to have a good guess about how much it is so that we can calculate the required sample size. There are several ways of estimating the expected effect size. One of them, of course, is to look into the literature for similar studies and see how much effect size is there. Or you can have a personal assessment of this, either by a good guess or by a pilot study, or you could try to think in terms of percentage how much you would think there will be a difference between the two groups, 10% or 20 or whatever. The third is to use the special conventions like Cohen's d for the effect size. Cohen had classified the effect size into 0.2 for a small effect size, 0.3 for a medium, and more than 0.5 for a large effect size. So if you have your thoughts about how much you would expect of a difference between the two groups, if it is small, then the effect size you can choose is 0.2, medium 0.3, and if it is you expect a large difference between the two, then you can choose 0.5 or more than 0.5. And if you don't want to use any of these three ways, then you can try and estimate the effect size with special formulas. The effect size can be estimated with the usual formula, but remember that we have not yet started the study, so you plug in figures here that you would expect them to happen. You've not seen the results yet. You would have a good guess about what you expect the mean of the first group would be, what you would expect the second group mean to be, and then you try and calculate the pooled standard deviation of the two groups using another formula. And once you have decided on the expected effect size, you can plug it into the equation plus the z-score for the level of significance and the z-score for the power. And this is just an example about what you can expect the effect size to be before starting the study. Say you have two groups here measuring a hormone or an enzyme or a certain continuous output. You expect the mean of the first group to be about 100 and the second group to be about 90, and you will use these two figures in the equation for the expected effect size. The tricky bit, of course, is the expected standard deviation, because that would require the number you would put into each group and the expected standard deviation for each group independently. And you can fill into this equation if you have sort of a rough idea about what you expect the standard deviation of the first group to be and the second group, and how much you think you would need in terms of sample size. And the equation first for the pooled standard deviation would start with the number in the first group, that's 100, minus 1, that's 99, multiplied by the square of the expected standard deviation, which is 20. So that's the first thing, plus the same thing for the other group. 100 minus 1 equals 99 divided by squared expected standard deviation, the square of 15 is 225. Divided by 100 here, 100 there, minus 2 equals 198. And from this you would get a figure divided by 198. This is 312, and you take the square root of this and it is 17.7. So you take the 17.7, which is the expected pooled standard deviation, put it into this equation, minus the mean. The expected mean for group 1 is 100 and the expected mean for group 2 is 90. So the difference is 10 divided by 17.7, and this will give you 0.56. So that would be the expected effect size. Use this into the formula, and now for the z-score for the level of significance, we use 1.96, and the z-score for the power we use, because we are choosing a 90% power, 1.28, and divide this by the effect size that we have just calculated, which is 0.56, and multiply all by 2. Then you get 2 multiplied by 33.5, that is to say you need 67 cases in each group. This is the other way of estimating the effect size from an estimated pooled standard deviation if you don't want to use figures from pilot studies or from the literature. One other scenario for measuring the sample size for controlled studies, continuous data, is when you are measuring the required sample size for matched samples. Matched samples is like, for example, if you are measuring the same person twice, one before and one after a certain treatment or a certain operation, or you have matched two individuals in any way and trying to see the difference of or an effect of a certain agent on them. So these measurements are for matched. We are interested more in the difference between the matched couple than in the pooled averages of each group. And for this, what we use in the formula for the effect size would not be the standard deviation, the difference between the standard deviation of this group and that group. It would be the standard deviation of the difference between individual pairs. So for the first pair, for example, the difference is 20 point something. And the second pair, you would find a difference of 15. And the third pair, you would find a difference of 10. And what we will do our estimation of the effect size of based on the differences, the mean of the differences and the standard deviation of the differences. So this would be the mean of the differences rather than the difference of the means, rather than the difference between the two means. We'll be taking the mean of the differences, and the same apply to the standard deviation. It will be the standard deviation of the differences rather than the differences between the standard deviation. And then we'll estimate the effect size, and that will be plugged into the equation as usual. A further scenario when we are trying to estimate the sample size for, again, controlled studies with at least two groups, a study group and a control group, but this time we are analyzing dichotomous data rather than continuous data. We'll be dealing with dichotomous outcome like alive dead, success failure, positive for a certain test or negative. We'll be using the same equation that we have used for the continuous data in the controlled study. The only difference would be in the calculation of the effect size, because there will be a different formula to calculate the effect size for the dichotomous outcome. Like if we are measuring, for example, ratios or percentages, not continuous data. We'll be looking into incidence, prevalence, same equation, but a different effect size. So first, we need to set up these parameters before we start the study in order to estimate the appropriate sample size. By far, most clinical trials and studies now use their two-tailed model, unless you have very good reasons to take a one-tailed model. The level of significance, which is again by far 95%, that is to say the p-value is equal to or less than 5%, and the z-score for this is 1.96. The study power, which is again how much you can tolerate a type 2 error, and for this the z-score is usually 0.84 for the 80% power and 1.282 for the 90% power, and these two are the most commonly used powers in clinical trials. The last thing is how much you would expect the effect size to be. That would depend on the difference between the two groups, the standardized difference between the two groups, that is to say the difference in terms of standard deviation. And for this you can do one of the following. The common ways of guessing how much the effect size could be before starting the study is either going through the literature and reviewing any prior research and get a rough idea about how much of an effect size between the two groups could be. You could also depend on your personal assessment of what difference is important in terms of length of stay in a hospital or amount of bleeding or rate of complication. Could it be 10% difference, 20, 30, or whatever? The third thing is to use a special convention like Cohen's d, and he classified the effect sizes into small with 0.2 effect size, medium with 0.3 effect size, and large effect more than 0.5 effect size. One other way to estimate the expected effect size is to use this special formula for the dichotomous data, which is based on the expected proportions of the two groups, the study group and the control group, and the average proportion between the two groups. So to give you an example, if we have two groups here for a certain success rates for a certain operation, in group 1 the success rate was 80%, the proportion is 0.8. Then group 2 success rate was 90%, the proportion is 0.9. The average success rate or proportion is 0.85, assuming that the two groups were equal in number. So the effect size here would be to subtract the smaller from the bigger value because of these two bars here. So that's 0.9 minus 0.8 divided by the square root of the average proportion, 0.85 multiplied by 0.15. So that will give you the number of 0.28 as the effect size. We plug this in here, and then this will be the z-score corresponding to the chosen level of significance for a two-tailed test, and this will be the z-score corresponding to the level of the power for 80% power. This will be 0.84, and the level of significance z-score will be 1.96 divided by the calculated effect size, which was 0.28, all squared and multiplied by 2. This will give you 200 cases are required for a sample size in each group. We've been through formulas for different scenarios in which the population was not known or was deemed to be finite or very high. This is a new scenario where we know the number of the population. Say we are setting up a study to find the proportion, the percentage of workers in a factory who have developed sensorineural hearing loss. The factory workers are say 5,000. This is a known entity. You can know that the workers here are 5,000, 10,000, or whatever. And the same applies for a study for estimating the hepatitis positive students in a college. The number here would be finite rather than infinite or unlimited population. So we need a new formula, and this new formula would depend on two things. Would depend on the estimated number for the sample size if the situation was unlimited, like the previous two examples. We just calculate the required sample size, assuming that the population is unlimited with the usual formula. And from this, we put this in here, and then divided by a certain other formula. And because we are dividing the number for unlimited population by something else, by another quantity, this number will be reduced. So rather than have the whole estimated number for the unlimited population, you would have a smaller number. We'll see that in the next. So in this example, we are starting to study the percentage in a finite population, like workers in a factory or students in a college. We start by estimating the sample size required in this situation with assuming just assuming that the population is infinite, like the original equation, with the margin of error, with the level of significance, and the proportions. And once we have obtained that figure, say it is 385, then we use that figure, we divide it by a certain other entity to get out the required sample size for the finite population, for the known population of 5,500, whatever. So if the finite population is 5,000 and the estimated sample size for the infinite population is 385, we plug this into this equation. This is the sample size for the infinite population divided by a certain entity in here. This entity, so we put the 385 in here. This is the required sample size for the infinite population divided by 1 plus, we use this figure 385 minus 1 divided by the number of the finite population. That's the n. This is the 5,000. And because we are dividing the 385 by this formula, we expect the 385 to be reduced. And this is what happened. We obtain a 356.48. That is to say 357 patients are required for the finite population of 5,000 rather than 385 for the infinite population. By this, we come to the end on this presentation on the estimation of the sample size in 8 different scenarios with different equations and its modifications. Salam alaikum.